Let y equals f of x. The derivative of x can be written as f prime x, but also as dy over dx. dx is the differential of x. dy is the differential of y. The differential of x can be any non-zero real number. The differential of x is independent. F prime of x equals dy dx. From here we can easily get that f prime of x times dx equals dy. It means that the differential of y is dependent on the function and the differential of x dx. Definition: if y equals fx is a differentiable function, then the differential of x dx is an independent variable, and the differential of y dy is given by dy equals the derivative of the function fx times dx. For example, let's take the function fx equals 5x. dy is the derivative of 5x times dx, so it is 5 dx. Example: fx equals x to the power of 2. The differential of y is the derivative of x to the power of 2 times dx, which equals 2x times dx. Let's understand more differentials. The derivative of the function, if you want to use the definition as a limit, is the limit of the difference of the y's, which is delta y's, over delta x, which is the difference of dx, but the difference of the x's has to be very small, so delta x approaches 0. And that's why it can also be written as dy dx. The derivative of a function y equals fx is the change of the y's, the rise, over the change of the x, which is the run, when the change of the x's is small. dx is the change of x, dy is the approximated change of y. The real change of y is delta y, which is f of x plus delta x minus f of x. Example: fx equals x to the power of 2. Find the real change and the differential of y when x changes from 2 to 2.1. The real change in the function is the function after the change minus the function before the change. So it's f of x plus delta x minus f of x. It's f of 2.1 minus f of 2. In this case, we get 0.41. This is the after. This is the before. If I would like just to approximate that change, then I can find just dy, because it is easier. dy is the derivative of the function times dx. Why dx? Because dx is x plus dx minus x. So in this case, it is 2.1 minus 2. And the derivative of the function is 2x. So I get 2x times 2.1 minus 2. Look what I did. I substitute 2 for the x, not 2.1, but 2. And I get 0.4. Example: y equals fx equals x to the power of 2 plus ln of x. We want to assume that dx is 0.1 when x equals 1. We would like to find what is dy, the differential of y. dy is the derivative of the function times dx. In our case, it is the derivative of x to the power of 2 plus ln of x times dx. The derivative is 2x plus 1 over x times dx. Now it's time to substitute numbers. X is going to be 1 and dx is 0.1. I'm going to replace all those x's by 1 and 0.1 for this. And I get 0.3. dy is only approximation for the real change, which is delta y. What is the exact delta y? I will write an expression, but I don't think we'd like to evaluate this one. It's the value of the function after the change. X was 1 and dx was 0.1, which means that f of x plus dx is f of 1.1 and f of x is 1. Each rule of derivative has a matching rule of differentials. Rule of differentials. If f and g are both differentiable, then the differential of f plus g is the differential of f plus the differential of g. The differential of f minus g is the differential of f minus the differential of g. The differential of k constant times f is k times the differential of f. The differential of a product fg is the differential of f times g plus the differential of g times f. The differential of f over g is, look at the quotient rule, the differential of f times g minus the differential of g times f over g to the power of 2, provided the g of x is not 0. If you want, you're welcome to use rules of differentials, but you can also use the regular rules for derivative, because the differential of a function is the derivative of the function, should just differentiate the function, and then multiply by d of x. Example, find the differential of x to the 4 e to the x. We are going to use the product rule for differentials, which is exactly the same product rule as for functions. Instead of differentiate the first times the second, we will take the differential of the first times the second, and everything the same. So let's do that. It's the differential of x to the 4 times the second function e to the x plus the differential of the second function e to the x times the first function. The differential of x to the 4 is 4x cubed dx, so we are replacing that. And the differential of e to the x is e to the x times dx. And we get e to the x times 4x cubed plus x to the power 4 dx. But again, why to bother with rules of differentials when we can just do it in a different way? I would like to recall that the differential of a function is the derivative of the function times dx. So I'm now using the product rule for derivative as usual. Derive the first one times the second plus differentiate the second times the first times all of that dx. And I get that, obviously, exactly as before. Find the differential of x to the power 4 over e to the x. Now I'm going to apply the quotient rule for differentials. Differential of the first times the second minus the differential of the second times the first over the bottom function to the power of 2. And I get that because the differential as before of x to the 4 is 4x cubed dx, and the differential of e to the x is e to the x dx. I get that. I can simplify a little bit. I can cancel one of those e to the x at the bottom with e to the x on the top. And I get that. Obviously, I can again do as before. I can just differentiate x to the 4 over e to the x and multiply the result by dx. So here is this. I apply the quotient rule. I got that. And in the end, I just added the times dx. And here it is after simplifying.